Thank you all for being here. I'm really excited to tell you about these new populations of small bodies that we've been focused on in the solar system, interstellar interlopers and dark comets. And this is all work that it's been very exciting in the last couple of months, but has been led out of the Department of Physics and Astronomy here at Michigan State. So for some broad motivation for why we scientists and astronomers like to study comets and asteroids within the solar system is the first real argument for studying them is that we can use these small bodies to trace the history and evolution of planetary systems and our solar system and recently exoplanetary systems throughout the galaxy. You can see here on the slide, you have a wide variety of types of small bodies, things like comets. This image of a comet, a spacecraft-ish image, shows that comets have ice in them. So when a comet gets close to the sun, what happens is the ice outgasses and produces an outflow, and you get dust comes along and you get this beautiful cometary tail that people probably are familiar with. We also have near-Earth objects, which are potentially hazardous objects, and mostly asteroids have no tails whatsoever, at least we thought. And then you have objects out past Neptune called the trans-Neptunian objects. But one of the actually key reasons that we study all types of asteroids and comets is that they are capable of delivering things like water and organics to terrestrial planets like the Earth. So these asteroids and comets can actually deliver prerequisites for the development of life to planets. Typical comets in the solar system, like the one depicted there on the left, have what are called cometary tails. Those tails are associated with non-gravitational accelerations. This is basically just what happens to a rocket ship. You have outgassing of gas, and that will produce a rocket-like recoil. A Oumuamua, though, you can see on the right, that's a deep image of a Oumuamua. There's no tail whatsoever, but it accelerated like a comet. So it basically broke all the rules of comets and asteroids. And that actually has led people to say that perhaps it was an alien spacecraft. So the reality is that that's not true, and the truth is much less fantastical, but it is still very interesting. We have, since Oumuamua, found a bunch of objects throughout the solar system, which also now we've discovered have no dust tails whatsoever, but are accelerating like comets. So what we think with Oumuamua and these new objects, which I call dark comets, is that they actually are outgassing material. So they are icy material. There is icy material in these bodies. They just don't produce the beautiful dust tails. So there could be many, many more of them in the solar system. Just about a year and a couple months ago, we published this paper outlining, once we started finding these objects, they just started popping out of the data. So we have over 14 of those objects now, these dark comets. And you can see on the left, that is a zoom out of all of the dark comets that we know about in the solar system. And on the right, that's a zoom in. So there's actually, now it's clear that there are two distinct populations of these dark comets within the solar system. You can see Jupiter's trajectory on the left in red, and then the Earth is in blue to give you the sense of scale. And the two populations are shown in red and gray orbits. I call them outer and inner dark comets. Maybe not the most inventive name, but the outer dark comets have kind of larger orbits further away from the sun. Okay, but the real star of the show is 3I Atlas, because that's what everybody has been interested in since July 1st. So, and it is exciting. So I led the discovery paper of 3I Atlas that's out of MSU with a bunch of MSU collaborators. It was discovered, though, the fourth author of the paper is part of the Atlas survey, Larry actually spotted the object. So this was on the night of July 1st, just in time to ruin all of our July 4th weekend. You can see here, this is the actual data that Larry was looking at in Hawaii at the telescope. So what you're seeing, that sea of stars, that little dot in the red, that is 3I Atlas. And then it moves a little bit to the right over about an hour. That's telling us that that object was moving very rapidly across the skies. So there is our first objective within about 12 hours, what we had to figure out was, is this really a new interstellar object? So you remember with the Oumuamua, right? You figured that out by seeing that it was on a hyperbolic trajectory. So with collaborators in Hawaii and NASA and the European Space Agency, we basically got as many observations as we could of the object to figure out its orbit. And we figured out within about 12 hours, the paper was almost written at that point actually, but we figured out then that this was for sure our third interstellar visitor. And so what you could see, the trajectory here, if you could see it, Atlas came in, I'm gonna play it, restart it. It comes in July 1st, that's when it's there. It has this close approach to Mars in October. Then it gets very close to the sun and the Earth. That was in December, January. And now it is leaving the solar system heading to Jupiter. Our second objective, this is now like 24 hours after it was discovered, was to figure out if it was a dark comet or an active comet. So does it have a cometary tail? Because that was going to totally change the approach we were going to take with our telescopes to get follow-up observations. And I'll highlight here work from Tessa Franke, who is a first-year PhD student at MSU in our physics and astronomy department. But Tessa was brave and started her PhD early. So she started mid-June, 2 weeks before 3i Atlas. And so 2 weeks after Tessa started her PhD, she was thrown into a crazy kind of zoo of, we had the discovery paper, but we are here at MSU, we are a partner in the SOAR telescope. So Tessa, within 2 days, got images, some of the earliest images of 3i Atlas with our SOAR telescope. We're partners in here. You can see that animation here of 3i Atlas moving across the sky. That's Tessa's data. And what that told us, you could see in the left image, there's this very, very vague hint of a tail. That is clear evidence to comet scientists of a cometary tail. So then the third objective, remember with this trajectory, 3i Atlas got very close to Mars in October. It doesn't really get close to the Earth, but it got very close to Mars. So we have this brilliant undergraduate here at Michigan State named Atsuhiro Yaganuma, if I can get to the right slide. So Atsuhiro basically has now written, he is applying to PhDs. He's a senior, but he was a rising senior at the time. He has published 2 first author papers about 3i Atlas. And what he showed within 3 weeks of the discovery was that NASA, what we wanted to figure out, could NASA send a spacecraft to visit 3i Atlas in situ? And so because it got so close to Mars, Hiro showed that you could take one of our existing spacecraft at Mars and get to 3i Atlas if we went before October. And those spacecraft exist. NASA has space-based assets at Mars, both in orbit and on the ground. So we had spacecraft that could go. That didn't end up happening, but NASA did prioritize 3i Atlas, and every space-based asset effectively has observed Atlas. And the exciting thing about Hiro's work was he demonstrated the feasibility of this. We should be finding many more of these interstellar objects now that Rubin Observatory is online. And when we have more of these objects, now we have proof of concept that we'll be able to get there from various locations with our spacecraft within our solar system. Our final objective was to figure out, where do these interstellar objects come from? And this is work that's led by Hayden Monk, who is also an undergraduate here, now a senior at Michigan State. A really nice paper that's under review right now. And this animation is showing you what a possible origin for an interstellar object like Oumuamua or 3i Atlas is. So in this, as a spoiler, this animation goes for more than 100,000 years, so we're not going to sit and watch the whole thing. But the blue points, those are ice giant. This is a real exoplanetary system. So this is a system called HR 8799. It has 4 ice giant planets, all more massive than Jupiter at very large distances. And what they showed is that these giant planets throughout the galaxy are very good at ejecting comets. So all of the particles are comets, just like 3i Atlas or Oumuamua, and the giant planets, after a very long amount of time, but you could see they're constantly kind of getting stirred up with the gravity of these planets. All of these objects after 100,000 years get ejected. So really, these interstellar objects are telling us potentially about building blocks from exoplanetary systems. So I'm going to leave my conclusions here. We have discovered, led out of here at Michigan State, 14 dark comets that have non-gravitational accelerations but no tails. We have identified now 3 interstellar interlopers passing through the solar system through Atlas. The discovery was led here at Michigan State, and our future observations of dark comets and interstellar objects can potentially answer questions about the development of life, both here in the solar system and in exoplanetary systems. So thank you very much for listening.
How big are these things? Like, how big is Oumuamua? Were you guys able to figure that out?
Yes, that is an excellent question. So the trick is that you can roughly figure it out if you assume something about how reflective the surface is. Okay. But we do know that it's got to be between not reflective to 100% reflective. So, and we know how there are asteroids and comets that we have other measurements of that reflectivity, so that we can kind of calibrate things very well. So Oumuamua was very mysterious. It was about 100 meters in size. But it also had a very strange shape, which we inferred from its brightness variations. It actually has a 6 to 1 pancake-like shape. That is another one of these very mysterious things about Oumuamua. I have some theories explaining that shape, but we don't really know for sure. The dark comets tend to be all the way down to 10 meters to hundreds of meters to even maybe 10 kilometers. But the smallest ones, those 10-meter bodies, there's actually one dark comet that, because these 10-meter bodies are of interest for lots of planet formation reasons, JAXA, the Japanese Space Agency, is already visiting one of our dark comets in 2031. So we will have space-based measurements of a dark comet.
There's like a world in which people could be up there and like touch.
Yes.
That's so cool.
Yes, when I have, yes, I'm glad that you think that. I also think that's really cool, but that was the message. And 3i Atlas, we just got a measurement with HST that showed that it's about 1 kilometer. So it is actually much larger than expected. So that actually so why this is, it's actually the key measurement we try to make is how large the nucleus of a comet is. You actually never see the nucleus, so it's really difficult. But now that we know that, for a few steps of logical reasonings, you can infer that there's, now we now know from that size measurement that there is one or more similar Oumuamua 3i Atlas objects moving inside of Earth's orbit at any given time. So we will be finding many, many more of these now that we know.
One more promise. For the dark comets, how do you guys know why there's not a tail? Like, have you figured that out? Like, what's causing? Sorry, this could be like a whole.
No, I mean, that is the question. So that's maybe why. I mean, if we answered it, then maybe you don't call it dark comet anymore. So, but that is the question. And that was the same thing with Oumuamua. Why was there no tail? I believe what I think is going on is that we have this observational bias, which basically means a reason we haven't been detecting them before is that we have historically, comets have pervaded our history, right? So we have always been very sensitive to finding comets because they have tails. So I think what's going on is that there are all of these other objects in the solar system that are comets, but for whatever reason, they don't have tails. That's why we haven't really spotted them. There's lots of possibilities. One idea is maybe these are comets that are almost at the end of their lifetime. So they've basically lost a lot of material, gotten rid of all of that dust, because the tails are all dust. Maybe you got rid of all of the dust on the surface, and now there's only gas coming off, which you actually wouldn't see. So that's potentially why. We have theories about Oumuamua, which are somewhat different, because that one came from the interstellar medium, but that is what we are basically trying to get JWST observations, and we have this JAXA space mission that's going to a dark comet. We're hoping that those will answer those questions, not just me putting out theories that take it or leave it, basically.
Thank you for making that easy for someone like me to understand. The whole reason I went into James Madison College is because I never had a great science teacher like you. I really appreciate this. It's really fascinating to me. This is probably a really stupid question, so I apologize. But, you know, you're talking about these comets doing their, what'd you say, hyperbolic?
That's right.
Yeah. So what is accelerating them, and why aren't they losing acceleration if they're not pulling off the gravitational field of other planets?
Basically, so for Oumuamua and 3i Atlas are these on hyperbolic trajectories. Oumuamua had a non-gravitational acceleration. What that means is that I should have clarified this. So this is a very astute question, actually. So that means that the acceleration that was measured of Oumuamua non-gravitationally, that was in addition to all of the gravity it feels from all of the bodies in the solar system. That's why it's so hard to find these non-gravitational accelerations, because first, you have to account for everything in the solar system. So our collaborators that we do these, the reason it's so difficult to find the dark comets in the first place is that NASA and ESA basically have to track the orbits of every object we know of in the solar system to account for the gravity of everything. And that is actually the reason that is mission critical, is either for tracking things that could potentially hit the Earth, and also if we're going to send a space, like we went, OSIRIS-REx went to Bennu, when we get a spacecraft to a small body, you need to know its location to centimeter precision. So that's why that's so important. The hyperbolic trajectory basically is accelerating from the sun. So it comes in, 3i Atlas, for example, came in at something like 55 kilometers per second, but it accelerated a huge amount from the sun. It's just with Oumuamua, You know, it actually went from 26 kilometers per second to 88 kilometers per second when it was at closest approach. That non-gravitational acceleration was in addition to all the other acceleration.
It's amazing to me it doesn't get captured by the sun's gravity because it's so tiny compared. I imagine it has something to do with the speed it's coming through and the angle it's coming through.
That's exactly right. The physically intuitive way to think about it is that these objects are moving really fast through the galaxy. The sun is also moving through the galaxy. And so the sun actually kind of intercepts their orbits, and then they come and leave. The reason they don't get captured, it's a very astute question because a lot of people have been working on the possibility that some of them do get captured. But what you need for a capture of an interstellar object is a third body. Jupiter is kind of the most massive thing, so Jupiter is actually capable of capturing some. But in general, the way you want to think about it is like if you can imagine a small particle that rolls down a hill and goes the other side, if you start the particle out of the hill and then you let it come down, it'll fall all the way down. This is just a changing potential energy to kinetic energy, but you're basically go all the way down, you're moving fastest when you're at the lowest point, and then you come back out and you leave. So if you start with enough energy to be unbound, you can never have, basically something has to happen for you to lose energy to be bound. That's kind of all that's going on.
Real short. It amazes me that you see these things, you're staring off into infinity, right? It's a person or a computer, and you're finding 10 meters. What's 10 meters when you're looking at infinity? Like, is it literally someone noticing movement that's watching one day, or is it a computer model picking up something that directs people to look there?
I really like the way you phrased it of looking out at infinity. It's a cool thing about astronomy is that we are always pushing the limits of our like sensitivity with our telescopes. So we have telescopes that can look down to some brightness. And in some cases, things that are very, very bright at many, many light years away appear dim. But you can have something that's very close to Earth, and then if it's 10 meters, it appears roughly as dim. So really as humanity, we are basically increasing the how dim we can look, but that could be something like a near-Earth object that's 10 meters or something that's hundreds of millions of light years away. For the near-Earth objects themselves, the reason that they are kind of difficult to find is that, so what you have to do, the reason they're difficult to find is you have to look at the entire sky every night because they're one of the only things in the sky that changes. So most of our stuff in our universe doesn't actually change on human timescales. Near-Earth objects and comets change on geophysical timescales. And one of the ways in which they change is that the Earth is moving, they're moving, and so they move very fast through the sky. Oumuamua actually came very close to the Earth. It was 40 times the distance to the moon, between the Earth and the moon. So we're looking for these things basically every night as they move through our telescopes. Most of that funding actually comes from DOE and DOD because of planetary defense reasons. It is, up to this point, it is mostly human identified. They do have algorithms to then, once you see something moving, try to kind of link the orbit together, but we have to spot them. And there's people all over the world, basically, even amateur astronomers will spot these objects that move and then submit them, and then we try to link them up. And I am almost sure, we have actually people in physics and astronomy working on this right now, one of my new graduate students. I'm pretty sure that we are, I mean, maybe I shouldn't say this publicly, but we are not that great at doing that linking, especially for interstellar objects. So the things that move really fast is very difficult for us to identify because you could imagine we're reliant on these things moving across the sky over a couple nights. If it moves so fast, it could just be gone in the next night. So I think that's why we basically missed objects in the past. But that means that there's hope for the future.
Science fiction fan in me is telling me you are wrong about Oumuamua, and that is an alien probe, and we just don't recognize whatever kind of life form that is.
Well, I have heard that comment many, many times. So I get emails about that like once a day. So
I'm going to echo what Trustee Barhart Cook said. My comment was going to be, thank you very much for dashing the hopes that I've had since I watched Twilight Zone as a little girl, that there are spaceships and flying saucers coming to Earth with ETs in them. So yeah, thank you. This was fascinating, however.
There were scientists that were saying that maybe it's an alien spacecraft because the reasoning for that is that you can explain the non-gravitational acceleration without a tail if it's either got rockets or if it's just like a light sail. So I think there have been ideas for hundreds of years that if you if you populate the galaxy with light sails, basically you could get really far because if they're really, really thin, the solar radiation, the sun's photons will basically just push it, just like a sail here on Earth. But yeah, I mean, there is no actual evidence for that. It actually, the light sail doesn't even fit the light curve of Oumuamua. Remember I said it had that pancake shape? That came from looking at how it actually changed its brightness very dramatically overnight. So that is, we can basically see how its brightness changes. You're basically just seeing if it's elongated, like if it's like my phone, it's basically like sunlight hits it and reflects back. And if it's tumbling, once you get a projection like this, you'll get much less light. So that tells us we actually got the shape. So it's 6 to 6 to 1, which is more dramatic than anything we've ever seen in the solar system. But it is, you would need like 1,000 to 1 to make the light sail work. So that's pretty much ruled out at this point.
Well, Dr. Seligman, we're love the passion you bring to this topic. I want to also acknowledge that you had students as part of your presentation, and we're trying to engage students in research. And thank you as a faculty member that obviously believes that that's important, and you're engaging them in your work. I have been wanting to get to the SOAR telescope. I know I know this consortium. I've known about it for years. As UNC Chapel Hill is also a member of that consortium. But do you think we could take the board on a field trip at some point? Is this one's in Argentina? Is it in?
Yeah.
It's in Argentina.
In Chile.
Chile.
Do we have the budget for that, Board Secretary?
If you want to go, I will help
We'll
you.
do a field trip to
I will
Chile.
go on the field
Okay.
trip with you.
Great.
Sounds like a
Sounds great.
plan.
Well, again, thanks for an incredible presentation. We learned a lot, and
Thank you.
keep up the great work.
Thank you. for
Thank
having
you.
me.